Today we're going to talk about friction and about the normal force. We have already used the weight, which is the force of attraction between the Earth or any object on the surface of the Earth, which is given by mg. M is the mass and g is the gravitational acceleration, remember 9.8 meters per second squared. But when I'm standing on the floor, I am feeling a force, which is my weight, which is pointing downwards, but I feel no acceleration, so there must be another force. Because of Newton's second law, we know that if there's no acceleration, the net force has to be zero, so there must be another force pointing upwards, which has exactly the same magnitude as my weight. That force is going to be called the normal, and it's normal because it's always perpendicular to the contact surface. When I'm stepping here, there's a force of my weight pointing down, but I'm not going through the floor of the building because there's a normal force pointing upwards. The force of this object, the weight, is this force here pointing down, and there must be another force, which is the normal, which is applied at the contact surface, which we call it the normal force. There is always going to be this normal when we have two surfaces in contact. In this case, because these are the only two forces here, if we apply Newton's second law and we know that there is no acceleration, we have that all of the forces, which is the weight plus the normal, has to be equal to zero because there is no acceleration. So we have that the weight is minus the normal. So, and this, remember that was mg. So we have that in this particular case, the normal is minus the weight. So there's exactly the same magnitude, mg, pointing upwards. This doesn't need to happen every time, so it depends on the particular problem, depends on what other forces are acting here. But we will always have a normal force when we have two objects in contact, and that normal force will be right at the surface of contact between those two objects, or the objects on the surface, or whatever. We could have another object here, and then this small object will have its own weight 2 and its own normal 2, where the subindex 2 is making reference to the object 2. Let's talk about friction. Friction is a force that appears when we have two objects in contact and one of them tries to move, keeping contact with the other object. For example, if I push this book across the table, I have to apply a force to make it move, but I'm applying a force now and the book is not moving. I'm going to increase a little bit more the force and the book is still not moving, and finally, if I increase enough the force, the book is going to be moving. So I'm applying a force, but I see no acceleration. That means that if the book is moving with constant velocity, it's because there's another force pointing backwards to compensate my force so that the book moves with constant velocity and no acceleration. So if I push not enough, it won't move. So there's a force going there that is opposing all of my force here. If I push enough, I can move it, but you can see that the velocity is constant, so there is no acceleration, so the net force is zero. So there is a force of friction between both surfaces that is opposing the force that I am applying. In order to explain this friction force, we would have to go to the microscopic level and see what are the interactions between the electrons and the surfaces of both objects. And we see that we have seen that by pushing the book, I was pushing with not too much force and the book was not moving, so there was another force opposing. But when I gave more force, then there was still a rest, so the force that is opposing was increased. So until I reach a boundary, a threshold, and then from then on I could move the book. So this means that this friction force, and this is an experimental result, we know that the force of friction F sub r is smaller or equal to mu n. So the force of friction is going to be smaller or equal to mu, which is a friction coefficient, and it has no unit, it's unitless, and n, which is the normal force. So that's a force, we measure that in newtons, that's another force, we measure that in newtons, and mu has no units. And what does it mean, this smaller or equal? Well, it means that if there is a surface, I have an object here with its weight, its normal, and if I'm pushing, I'm applying a force here, there's going to be friction which is going to be opposing that. So there will be a force of friction going back. And if I increase this force and make it a little bit larger, this will be a little bit larger also, until we reach a limit, where the limit will be when the force of friction is equal to mu times n. And then we begin to move that. So this friction force depends on the applied force. It's not a constant value. It is increasing until I start to move it. So indeed, we can write this expression as force of friction is going to be smaller than mu s n, and force of friction is going to be equal to mu k n. So what is this s and k? So this is static and this is kinetic. So it means that this is a friction coefficient, static, which is different from this friction coefficient, and this is when the object is at rest, it's not moving. That's why the subindex is static. And this is when the object is moving. When it's moving, then the force is equal to this kinetic friction coefficient times the normal. So this is after static, and this is after kinetic. So when I was moving the book, it's because this is the equation that gives me the friction of the book with the surface of the table. Let's do a simple exercise on this. Let's assume we have an incline here, this is an angle alpha, and we have an object here. And let's assume it is at rest, and the first thing we need to do in this type of problems is to draw the free body diagram. And then first of all, we need to think about what are the forces. Well, we have the weight, we have the normal, and now we're going to have the friction. And if there was no friction, the object will be sliding down. So because friction is always going to be opposed to the motion, friction has to go backwards. So these are the three forces that we have. Let me just draw here just the forces without the object. We know that because friction is parallel to the motion always, and normal is always perpendicular to the motion, there's going to be an angle of 90 degrees here. But if this is alpha, we know that that is also alpha. So, well, here we can just apply Newton's second law and solve and find the relationship between these three forces. We will decompose into the x-axis and the y-axis, and apply Newton's second law in the x-axis and Newton's second law in the y-axis. So in the y-axis we have w pointing down, so that's going to be negative w plus, and that's going to be the normal, so this is going to be fr sine alpha, and this, if this is alpha, this is also alpha, so that this is going to be the cosine plus n cosine alpha, and there is no motion in any direction, so that's going to be 0. If it's at rest, and in the x-axis we have that negative n sine alpha plus fr cosine alpha is equal to 0. This is These are Newton's second law, the two equations, in the case that there is no motion. So acceleration is going to be 0. Now, let's see what happens right when the object is going to start moving. So what do I want to find? I want to find what's the relationship, at which angle, if I'm increasing this angle, what's the angle where this is going to start to move down. So if it's flat, I know that this object is not going to slide. If I increase a little bit, because of friction, there's not going to be any motion, but there will be a limit when this has to start to move down. I want to find that angle and see what's the relationship between that angle, alpha, and the other parameters of this problem, the weight, friction coefficient. So in order to impose that, I have this friction force here. Now what I'm going to say is that that friction has to be equal to friction times n. So I'm going to impose that Fr is equal to mu static times n. So I'm going to impose this, and then I know that that's the maximum friction force, and from then on the object is going to move. So imposing this, I will find the angle at which this is going to start moving. So I just substitute this here. I get these two equations, and from this one here I see that those two ends can cancel, can go away, and I have an expression between sine of alpha, cosine of alpha, and mu s. If you solve this for mu s, you find that mu s is equal to the tangent of alpha. So for that particular case, I have an object in an incline, there's only the weight and friction. I can measure the friction coefficient by just measuring the angle at which it starts to slide. But this angle does not depend on the mass of the object, it only depends on this friction coefficient. And what does that friction coefficient depend on? Well, it depends on the two types of surfaces that I have. If it's ice and glass, if it's rubber and concrete, if it's wood and wood. So for each couple of surfaces there is a different friction coefficient which depends on the microscopic properties of those two different surfaces, those two different materials. But it doesn't depend on the mass, the angle at which it's going to be starting to move. It only depends on the material that those two objects are made of.